On guys, let's look at this problem right here. This question is asking a beam of light is incident normally on a quartz plate whose optic axis is perpendicular to the beam. If lambda naught is equal to 589.3 nanometer, compute the wavelengths of both ordinary and extraordinary waves. What are their frequencies? Here we are going to find out the wavelength and the frequency of the ordinary and extraordinary waves. Here we have the lambda naught available, that is wavelength at vacuum. Okay, that's equivalent to 589.3. And also, if you remember, for ordinary we can use this equation, that is index of refraction at ordinary is equivalent to lambda naught divided by lambda ordinary. Okay, from this one we can find out lambda ordinary. If we rearrange this equation, this is going to become lambda ordinary is equivalent to lambda naught divided by no. And here we have the lambda naught available, that is 589.3 divided by the index of refraction at this wavelength. For the given material, here we have the quartz material at this wavelength, the index of refraction, you have to look at the table, you will get 1.5443. okay, so this is our index of refraction, and if you calculate this one, you're going to get, and also this is nanometer, nano is 10 to the power of minus 9, and if you calculate this one, you're going to get 3.82 times 10 to the power of minus 7 meter, and in nanometer that's going to be 382 or 81.6 nanometer, because I just rounded this one to 2 decimal places, but if you expand, you're going to get this one, 381.6 nanometer. Okay, so this is for the first part, lambda ordinary. Also lambda extraordinary, it's the same thing. You can say lambda extraordinary is equivalent to lambda naught divided by ne. The index of refraction doesn't change, and no is going to be, no is also same, but the index of refraction for extraordinary it's different, right? It's a little bit different. And if you look at the table, you will get 508, the lambda naught is going to remain the same, 589.3 times 10 to the power minus 9, and index of refraction for extraordinary is going to be different, like you will get 1.5533, before we had 1.5443, right? So this is going to give us 379.4 nanometer. So we have done the first part. The first question is asking to find out the wavelength, ordinary, extraordinary. We found out that one. Now we are going to find out the frequency. To find out the frequency, we have to remember two equations. You have to remember that V is equal to F lambda. This is one of the equation. And also we have to know that V is equal to C over N, right? Here, instead of this lambda, we are going to use lambda ordinary. And we are going to say this is V ordinary. And for this one, V ordinary, N ordinary, okay? Now we can equate, since we are trying to find out the frequency and velocity is not provided, we can equate these two equations. Like we can say F lambda ordinary is equivalent to C over N ordinary, right? Since we are trying to find the frequency, we can move this lambda ordinary to the other side. That's going to give us F is equal to C over N ordinary divided by lambda ordinary. Now let's go ahead and plug the values. C is equal to 3 times 10 to the power of 8, and N ordinary is, we know that from here, 1.5443, 1.5443 divided by lambda ordinary, that's going to give us 381.6 times 10 to the power of minus 9. Okay, and if you calculate this one, you're going to get 5.090 times 10 to the power of 11 hertz. Actually 5090 times 10 to the power of 11 hertz. Okay, yeah, so this is the answer for this one. Now let's go ahead and do that for the extraordinary. For extraordinary, we are going to have C over NEX over lambda EX, and C is going to be 3 times 10 to the power of 8. Okay, let's use a different color. F is equal to let's use here. Okay, F is equal to C over N Ex over lambda Ex, and here we have 3 times 10 to the power of 8 divided by Nex, that is 1.5533, 1.5533, and the lambda Ex is 379.4, 9.4 nanometer, that's 10 to the power of minus 9, and that's going to give you 50. Let's write this one here. 5090 times 10 to the power of 50. Okay, 5090, 5090 times 10 to the power of 11 hertz. Okay, for both of them we are getting the same answer, and that's how we do this kind of problem. So I hope this helps. Thanks for watching.